A chapter 12, a deflection of beams and shafts, part B, moment, area theorem, example number 6. So in this example, we want to calculate the delta maximum and also the theta at A for a simply support beam of AB and a distributed load of a two piece of triangles by the maximum value of W. So for solving this problem, if we just cut the half of the part through and just go for a length of x, so that's the length of x, and simply develop that's a solution one elastic curve equation from the moment. So we want to find the moment and get the elastic equation and deflection of beam based on moment equation. So it just says a, a reaction at each of the reaction, because the total length is a half of, then it just goes by a rectangular distributed load of WL. So if that was our situation, it was something like W. So each of the reaction goes by a WL over 2. But because our case is half of that, by simply looking to the geometry of the figure, our problem, you can easily find that it's half of that. So that's a WL over 4. RB are identical to RA, and that's a L over 4 as well. So each of them goes by a quarter of L. That consists of a half of WL, which is the combined load. So, and if you just consider the equation for M, so when it just goes by a L over 2 halfway through, that's a W. How about if I just stop at a distance like what we cut our section through, then that's a x. So in that sense, the intensity of load at the length of x is just a W times x over L over 2. So W times x over L over 2. And if you just rearrange it, it just gives you 2x over L times W. That's the intensity up to this point. And that applies at 1/3 from x by the, and if you convert the distributed load to a concentrated load, that's the area of this triangle, which goes by a half of x over L over 2 W times W, that's the intensity, times uh, x, which is our base. So that's our height. If that's the area of our, that's a half of height times base. Our base is h. Our height is the intensity of the load up to this point. And that's comes from here, 2x over L times W. And if right then, by simply developing the equation of M, can easily have your load that as Wx over 2 times W over L, Wx squared over L. That's our force, and which is applied at a 1/3 from the base. And if you develop the moment equation, it just gives you mx equal, if you rearrange this equation, if you rearrange it, it just gives you mx is equal to a negative w over 3l x cubed plus wl over 4 times x. First integration of moment, it just simply gives you theta, and the other integration, the second integration from moment, it just gives you deflection equation. By each equation, by each integration, a constant appears, and for each constant, again, we need a boundary condition. So that's just the equation from moment to theta by the first constant C1 and integrated once more, it gives you delta, and that's a C1 plus C2 by integration of theta to delta. So now by going for going for my bad, if we call that 1 and 2, and if we just go for the boundary condition, so in boundary condition we have a, again, this is 1, this is 2. One is theta equation and the other is phi. And our first boundary condition is at x equal to 0, delta is 0 here. And at the other one, at x equal to L over 2, b is says theta is equal to 0 at the halfway through at the center. So if we apply these two, so that says a 1 plus a 1 plus 2, a plus 2, a plus 2. If you replace a in 2, it just gives you a C2 is equal to 0. And simply by replacing the b in 1, so that's b in 1, a theta equation, it just gives you C1 is equal to negative 5WL cubed over 192. And then we have the whole entire equation for the whole equation for a theta and delta. So if you just look at the symmetry of a structure, you can easily see that delta maximum happens at x equal to L over 2. And if you replace that L over 2 in the equation of delta, it just gives you a y, or as delta max is equal to a negative WL to the fourth over 120 times E times I. At the same time, if you just want to know what is the equation for a delta for theta at each of theta A and B, you can easily replace that in theta equation. Over here, you know what C1 is, you can easily get the C1 is a noun, and you can easily get the theta. We'll get back to it. Let's solve the problem in an easier approach. So that says if you want to ignore the tedious integration process, you can solve the problem with the moment area theorem as well. So how that goes, it just says if I want to draw shear, that says my shear, it just comes up by the amount of RA, which is WL over 4. So it just come up by WL over 4. So, and it's just a linear, so that's a first degree. So my shear is second degree, 1 degree higher, because that's the integration of W. And if you want to draw the moment diagram, that's a, let's make it a bit cleaner. So that's a M maximum is equal to M maximum over here is the area under shear. So area under shear, we just know that's a 2/3 of height, which is WL over 4 times base, which is L over 2, the half of the length. So that gives us WL squared over 12 EI. And at the same time, we do know that's the area under shear. That's our delta maximum. And sorry, that's our shear maximum. And delta maximum based on second uh, moment area theorem is just a, so if this is deflected beam, as you can simply see here, that's delta max. And if you keep a closer look on that, it's just simply a, a tangential from A, and that's a vertical distance tangential deviation of A with respect to C, which is center. So if delta maximum is tangential deviation of A with respect to C, you have to measure x bar from A. So I need this distance. So, and that's a matter of if this is a third degree, I already know what my area is, m over ei. That's my m over ei times x bar. I need to calculate x bar this time. So my x bar is just simply this value. And this is m over ei for a third degree. Let's see how that works. So for x bar, I just need to calculate the centroid for a third degree parabolic spandrel, which I uh, I do know how to do this part, the parabolic expander like this, but for this one I need to calculate based on centroid concept. So what to do if you know this is a positive x direction, and I already do know for a third degree curve, this is a area of a smaller chunk, and that goes by if that's a third degree, this is a 1 over fifth L, that's 1 over n plus 2, and the area goes by 1 of a quarter of L times h, if the total length is L and h. And like previous problem, we just need to calculate the centroid for the bigger chunk of area, which is this part. We know the area for this part is a just a LH minus 1/4 of HL, which is a 3/4 of HL this time because that's a third degree curve. And but for x bar, we just need to do the mass like this. X bar is summation of AI xi over a summation of AI, and that's a subtraction of the total rectangle minus a smaller a parabolic spandrel by third degree. That's a HL, the total rectangle, minus times the centroid for rectangle, which is L over 2, minus a the area of this greenish area, that's a quarter HL times the centroid, which is a quarter of H over L. And in the denominator, just subtraction of the area, HL minus a quarter of HL. So if you do the math, it just gives you x bar is equal to a 3 over 5 times length, and that's a x bar. We already calculate the area under moment. We have a x bar. If we come back to our problem, it just simply says you already know what your moment is, your shear is. Your moment is a area under here, and that's a distance of we already know that what x bar is a 3 over 5 times the length, and our length is L over 2. So x bar is a 3 over 5 times L, which our L is L over 2. That's over here. And if you do the mass, it gives you the area delta max, which is T of A with respect to C is the area under moment time x bar, which is 3 over 5 times L over 2. And if you do the math, it gives you a approximation of WL to the force over 120 times EI. And at the same time, if you calculate the theta for each of them, you just go by the area under moment. It just gives you a delta max of a negative W to the force over 120 EI, and also a theta of equal to theta b, and that's a negative 5 L cubed over 192 EI. That's the result of a two simple support beam by a distribution of a two-piece of triangular loading of W. That's a delta maximum, that's theta A, and that's theta B. Delta max is equal to a negative WL4 over 120 EI, and theta A is equal to theta B due to symmetry, and that's a negative 5 WL cubed over 192 EI. We solved the problem from both integration and a moment area, which is far simpler. We'll solve more example in next video. Thank you.